The process of consolidation is the process by which essentially memories become stabilized and available for long-term usage. And our understanding of that process has been relatively sketchy. Up until the last decade, I think we've had a very poor sense of it. We know that it happens. People have long-term memories. They can access those long-term memories. But psychologists didn't even use the word consolidation too much. It really comes out of sort of the biology of memory. And it's about making memories robust and stable.
So the idea that sleep may be involved in memory formation has actually been around for, may be involved in some aspect of stabilization of memory, has been around for some time, but has been difficult to really study in an objective fashion. Really in the past approximately 20 years, there's been a series of studies mostly focused on in humans, behavioral studies in humans. Up till now, nobody had developed an animal model system that didn't have certain particular features that brought to question how general an observation it is. And what we were doing in this study was asking the question, can we generate such a system?
And so in that study, she basically designed a study and collected data on humans that showed that after training in the morning or training in the evening, a sleep cycle made consolidated essentially the perceptual learning of that synthetic speech. What was remarkable is that she demonstrated two kinds of findings. One was that after 12 hours of waking following training, people had forgotten or lost some of what they learned, about half of what they learned. So at the end of training, they were at about 20%, they showed a 20% improvement in performance. But 12 hours later, if they were awake, they showed about a 10 or 11 point improvement. But if they slept after that, they recovered those 10 points. So the next morning, they were back at 20% improvement. So sleep was able to recover learning that seemed to have been lost over the course of a waking day. Furthermore, by training people in the evening, testing them the next morning, and then testing them the following evening, she was able to look at what happens when a waking day follows a sleep cycle. So if the only thing that sleep consolidation did was to restore what had been lost over a waking day, then basically from the end of training one night to the next morning, you should see no loss, no change, and no benefit. But if that didn't stabilize memory, by the end of the subsequent day, you would see a loss of 10 points. But it turns out that the sleep cycle inoculated you against subsequent loss. So there were two things that consolidation showed that were showed as consolidation in that study. One was a recovery of loss over the course of a day, but the other was a prevention of subsequent loss over the course of the next day.
So with the first-person video game study, we wanted to follow up on the speech perception study. And at that time, most of the behavioral evidence showing sleep-dependent consolidation had really been using tasks that involved very simple skills, like typing a simple sequence or looking at a simple visual stimulus over and over again. The speech perception study was a more complicated stimulus set, but we wanted to continue in investigating how sleep related to these more complicated tasks. So first-person shooter video games was a really great task for that because it's a task that involves a lot of complicated visual stimuli that are constantly changing, auditory stimuli about what is going on during the task, and complicated motor movements with your hands and fingers doing different tasks all at the same time. Additionally, first-person shooter games are a task that people actually do. We use the starlings for this task because starlings happen to be animals that are great at learning these operant type of tasks, where we can just, in this particular task where we taught them to discriminate between different sounds, they're able to learn depending on how complicated the discrimination is, it may take them a very long time, maybe several weeks or months to learn one, or you can set the discrimination up so that they can learn it within a couple of hours. And that was really important for this particular experiment because we wanted to be able to show a small amount of learning in a short period of time so we could then test them after a retention period over wakefulness and then over periods of sleep. So we could really replicate the way the studies were done in humans to see the way the memory changes over a 24-hour period. So the bird is in this cage and it has a circle hole, a probe port that we call it, that the bird will poke its beak into, which is a natural behavior for the starling. And when the first time the bird sticks its beak into this hole, it initiates a trial. And the trial consists of one of two stimuli that will be played. Each one is a 5-second segment of a novel starling song. As in the human studies of the speech perception, the video game study, where performance declined prior to sleep over wakefulness, but not after a period of sleep, the starling performance only showed this tendency to get worse prior to sleep, but after a period of sleep, the performance remained stable over the course of the day. And so this was showing that sleep, on the one hand, consolidated the auditory discrimination learning in a pattern that was very similar to what has been found in these human studies, showing both an improvement over sleep and a stabilization after sleep.
So we're interested in asking the question, is there an animal model? Can we see this phenomenon in an adult animal where we're testing in a fashion analogous to what's being done in humans? And the fact that the answer is yes, first and foremost, suggests that this is a very, very broad general phenomenon that might be shared across a great many vertebrates. And secondly, allows us to examine mechanistically a phenomenon that now shares a similar behavioral pattern as has been seen in humans. So it was quite important to do that. And of course, you can do mechanistic and behavioral experiments in animals that are difficult to do in humans.
And that's an unusual situation. I think there are very few paradigms of research that have unfolded both at the same time in parallel between using humans and animal subjects, where one can do very precise cellular physiology and do large-scale cortical network analyses in humans and birds, and have parallel behavioral results that you can manipulate, control, and test.
This is a much tighter collaboration where results in one system really in a deep and fundamental way inform results in another one, so that you do something in Tweety birds and now all of a sudden you go, well, this gives rise to a very interesting experiment in humans, and you go off and do that, and lo and behold, you do a series of experiments and find some interesting results.